I'm going to hope that Bill's not muted. No, he is. All right, hold on. Ask to unmute. Bill, you can unmute
I
yourself.
did that already, yeah.
Okay, all right, good. Okay. All right, with that being said, let's get started if you'd like.
Sure.
Okay.
Um,
I'm going to put you on speaker view.
okay.
There you go.
All right. I'll just share my screen here, first of all, and we'll get going. All right. Can you see that?
Yep.
I'm gonna go I'll go right into the slideshow pretty soon.
Okay.
Find my cursor. It's on two different screens here. Okay, so you should see a full view of these three colonies. Is that right?
Yep.
All right, great. So I'll be asking you questions, Lynn, during the during the talk. Like, please respond.
Yes, will do. I see snow.
Yeah, okay, you're going to see snow. All right, great. Yes. So tonight's talk is about thermoregulation, and I hope you learn a little bit about how bees generate heat during this discussion, and then also a little bit about how they're naturally inclined to want to conserve that heat, and also how they do that, and how some of our beekeeping practices actually work a little opposition for what bees want to try to do naturally. And I'll explain that condition with what I'm calling a condensing colony versus a ventilating colony. We'll talk more about that later on. So this all started with an article I wrote in Bee Culture back in 2015. By the way, that's almost 10 years old at this point. And I got started. That's where I coined the term condensing colony, and it caught on. I'm a beekeeper in Connecticut, Cheshire, Connecticut. We have I would say a moderately cold winter time. I also have a background in engineering. I started out life as a mechanical engineering and then went on to computer science later on in my professional career. And then I picked up beekeeping. I'm into my second decade of beekeeping now, way into my second decade of beekeeping. I own a little apiary in Cheshire, Connecticut that we make artisanal honey. And I call it artisanal honey because we can get more for it that way. You make the same honey, but so start calling yours into artisanal also. You get more money for it. Because of course we all know you can't really make much money with with honey. I'm also the president of the Connecticut Beekeepers Association, where we have about 670 members. And I am EAS certified master beekeeper. And I also took Jerry Brumenshank's master beekeeping course at the University of Montana. I am the Connecticut's representative at the EAS. So I'm on that board also, and I teach and help and I assist with certifying master beekeepers that want to come up to our EAS and take a test. So I participate in the field and written in orals and that. All right, so let's talk about thermoregulation. Let me see. So I have this little thing with my throat. I'm going to apologize ahead of time. Okay, why can't I go here? All right. All right. So thermoregulation is really just a adaptation that bees have and have developed to live in temperate climates. And they use their indirect flight muscles to generate heat. And there's no real observable motion that occurs. And I'll explain a little bit about that. And you will see during the course of this talk and also on the recording that you'll see the scientific references that I state on most of the slides that you'll see. So all of them are based on research, which I've done an extensive amount on thermoregulation because it's a subject that interested me, and I put together these talks based on the science. So to actually see what we're talking about in terms of thermoregulation, we use infrared radiation, which comes off of all warm body bodies in the world. Any live animal gives off infrared radiation. We have cameras that can capture that. And the interesting part about thermoregulation is that it's graded by color and temperature. So you can see in this little diagram above, you can see the colder spots are a muted sort of red, and then the warmest spots are yellow. And in this case, it's a string of bees, and all of their little thoraxes are warm, and their abdomens are a little cooler. So that's what you can tell from there. But if you were to take a IR camera out, and this is just a little top bar hive that I've been running over the years. It's actually a nuke top bar hive, and I took this picture right around today, in 4 years ago, almost, well, 3 years ago, and it was 62 degrees outside. And when I took it in IR, picture of this box, you could see that the signature shows all of its heat profile, and also shows the bees, which you can't see in this. They're not as obvious in the photograph on the left, but those bees are there on the left on the landing board, but the IR photograph is showing them as the hottest part on this whole arrangement. Now, if you were to take that top cover off, you can see exactly where the cluster is inside that top bar hive. You can obviously nothing visual on the left, but the IR signature shows you right where the most heat is in that colony. So this is just to illustrate how valuable infrared radiation is in the study of thermoregulation for bees. And I'm going to show you some more. I'll be using IR photographs for the next a couple of slides. So that's why I'm showing it to you now, so you get the idea. All right, so bees are amazingly adapted to flight. They use their indirect flight muscles, and they vibrate their thorax. Their thorax are not, their flight muscles are not connected to their wings. They pivot on wonderful membrane material on the thorax. So that's why you can actually hold a bee's wings and not damage their musculature, because it's not connected to them. We use that technique when we fool around with queens and all of that. Now, so bees can fly like this, and I put some statistics down there because I think it's really interesting that they have this stretch activated musculature that can just work on intermittent signals from their brain, and then they can fly, at or move their wings at like 230, sometimes 240 beats per second. And of course, there's other insects that are way more capable of being able to move their wings. There's a midge that can move its wings 1,046 times per second. So flight muscles on insects are really important, but when you have to use them for heating, you got to stop that wing action. So what bees do is they have a couple of different neurological signals they can send to their flight muscles. One, of course, you just saw is flight, where there's a stretch activated response in the musculature that moves their thorax and they can fly. But when they want to use them same flight muscles to make heat, they have to lock the muscular down into an isometric state, similar to like a plank exercise would be. Or if you remember back in the day when there was a thing called isometric exercises, where they were encouraging people to do them at their desk at work, where you just tense your muscles, and so that we have that same capability. We can put almost any musculature in our skeleton into an isometric state. And bees can do the same thing. So they can hold their indirect flight muscles into this sort of suspended state and generate heat, a lot of heat. And you can see here that if you remember those temperatures from the first chart, which you probably don't, you can see that these are pictures of heater bees that are actually inside of a cluster making heat using their indirect flight muscles that they have put into an isometric state. All right, so heater bees are really incredible in that they can move the temperature of their thorax up into degrees over 100 degrees and almost in their into a state of fatality. So if they went up higher than 108 degrees or so, they can expire. But it certainly does do a little to age their musculature. So heater bees are taking a hit for the colony in some ways by acting as a heat generation source. You can see the little slide on the right. You can see the center looking down through, you're looking up through a cluster. Bees are around the combs. You can barely make them out. But in the center, you can see a bunch of heater bees in there that are generating warmth for the entire colony. Now, if you want to learn more about what your colonies are like in the wintertime, I suggest you look up this article by Owens. He was a wonderful research scientist. And I explain more about him in a minute, but he did an extensive study of the thermology. He called it of wintering honeybee colonies, 5-year study, and he got lots of data points. And those data points he used to make graphs. He had thermocouples, millions of data points, and over 5 years. And he's the one who basically outlined for us that the temperatures that colonies stay at in a winter cluster. He's the first one that on record that I know of that did this kind of an extensive research, and it came up with the idea. That's what, when we talk about temperatures in the cluster today during the winter, we're talking about Owen's work. All right, so this is a film I want you to see of actual heater bees in motion. You can see there they are in natural light, and then we put that in IR, in an IR camera. You can see, and a little close-up, you can see bees moving around. Here's an individual heater bee in the middle of a cluster. Notice again, abdomen cool, and its thorax really warm. So a heater bee would normally be down in a cell with its head down in a cell. You can see how it emerges from that cell. You can see how it actually works. Oh, and here's trophylactic feeding, because heater bees need a lot of food to continually generate heat, so they get it from other bees. And here's shown that heater bee was getting fed by another bee, carbohydrate, of course, to keep the colony warm. All right. So what I'm trying to illustrate here is that there's a profound effect with heater bees, even at low levels. It says we don't have a lot of heater bees active all at once in a winter cluster, in the center of the core of the winter cluster. If you look at the slide, the photograph on the right, it's not actually a photograph, it's just a graphic on the right. You see one heater bee has that sort of influence around the cells right around it. So it's not a very big influence. But if you gather together 5 or 6 heater bees in that same center of the cluster, you can see that they have a more profound effect on the amount of heat that's generated and dispersed in a large circle around those heater bees. So it doesn't take a whole lot of heater bees to maintain temperature in a cluster. What you should know about wax, because this question comes up from time to time about how bees are hanging around in the cluster, and how much energy does a wax cell take up, and how does a wax cell interfere with the heat transfer. And the studies indicate that they are it's virtually transparent. In other words, as far as the transfer of heat around in a comb, a honeybee comb, it might as well not even be there. Bees are just hanging on a scaffold of comb, and the distribution of their heat is unaffected by whether or not it has a plastic foundation or natural wax comb. It's just a scaffold where the bees hang out and heat. All right, so part of Owen's 2 million data points that he collected over 5 years, he actually took them and summarized them in this one little figure that you're looking at here, which he called figure 2 as part of his study. So this represents 2 million data points over 5 years. So it's an incredible amount of research. And he indicates there what, if you look in the center, you'll look at the center temperatures at the peripheral in the 80s, but around in the center. This is when, by the way, when a colony has brood in it. And the center is in the 90s. And then as you go away from the center, the temperature profile thermoclines change and the temperature goes down. Now, what Owens didn't address, and we have begun to understand later on actually in the last decade or so, is that above a cluster, this all-important heat dome that I have a little circle on there occurs. So in other words, there's a stream of air, hot, moist air, or warm, moist air that comes out of a cluster, assuming that it has enough porosity to allow that air to go through, and then it's captured as a dome above the cluster. So it's basically a fancy way of saying there's warm air above the cluster. All right, so look at that study if you're interested. All right, so the takeaway from this is where we got our central understanding of the cluster's core temperatures, and also later on we've learned that there's an all-important heat dome that occurs above the colony, and you can actually see that in this picture. You can see below the colony the temperatures are in the 30s and 40s, and then eventually it's almost ambient temperature a couple of inches below the bottom of the cluster. But if you look on top, it's 70s, 80s, and so forth. That's reflected in the dome. All right. So according to our own anecdotal experience and Owen's work, we know that the outer mantle lower limit is somewhere around 43 degrees. And after that, bees will go into a chill coma, and most will die after 50 hours. But a chill coma can last for a long time, and it can fool you as a beekeeper. You might go out in the wintertime this winter and see some bees that are in the snow in the front of your colony. And if you picked one of them up and you put it in your hand and you blew your warm air on it, you might even be able to revive it because it might just be in a chill coma. So you can actually experience a chill coma if that's what you're inclined to go out and do during the wintertime. And then the inner core stays around 70 degrees if there's no brood, and it goes up, of course, to around 95 degrees when there is brood. Now, we've been, I think, under the misconception for quite a while that we have an extended broodless period that occurs in our colonies. Now, we've known since the 70s that it wasn't true, but the sort of bee lore defied that and continued to talk about the mythology that we have an extended broodless period, but we don't. We might have a week or two of broodless activity at the end of November, but sometime around or the first couple of weeks in December. But the first, right after the winter solstice, queens start to lay again. So you have a little bit of, and if you have like a broodminder thermometer or something over the top of your cluster, you'll notice that. You'll notice that the temperature will rise briefly in fits and starts, because all through December or through the latter part of December and all through January, the queen's laying. And depending on the colony strength, its amount of stores and all of that, the amount of brood will vary between smaller and larger colonies. But by the time February comes along, we're back into full brood rearing, and the core temperatures are high. So that gives your bees some ability to be able to break cluster on their own on warmer days, and then go find other food in the colony and gather around, and they stay around the brood, but gather around those other food sources and bring them back to the bees that need them to keep the colony warm. Right. So that has other implications with mite control too, but we're not going to get into that. So it's hard to find data that supports the movement of bees from the mantle to the core. We do know that it happens. And what it's actually based on, is it a emerging property of dehydration, or is it actually a need for bees to go get warm? There's both of those theories around which one is true, or which one is more likely to occur naturally, or does occur naturally, is an interesting study. Now, there are some studies where they have painted bees or dotted bees on the cold part of the mantle, which is the outer part of the mantle, and they've also done the same thing to bees they found in the core, put little dots of paint on them, and then went back and looked and see if they're scattered around, and of course, yes, they are. So they do move around, but why they move around, we don't, or what the mechanism is that sparks them to change the morphology of that winter cluster is still one of those mysteries in beekeeping. So anyway, if you wanted to read more about this, ABJ reprinted that article that Mobus did back in '98, which is a really interesting thing to read about. He calls it Rethinking the Cluster, and his theory is that it's about they're driven by water needs, because mantle bees are using a lot of energy, and so their metabolic rate is higher than bees in the cluster. Although it seems as though that wouldn't be the case, because you have heater bees in the cluster, but most of the bees in the center of the cluster are in a warm environment and are doing very little to thermoregulate. Bees on the mantle are the guardian of the cold air coming in or around the cluster, so they're trying to keep their outer mantle limit above 43 degrees, and I think they settle somewhere around 46 degrees. But so they're going to use energy to do that. They build up a lot of metabolic moisture, where the bees in the middle are dry, the bees on the mantle are wet. And so Mobus's theory is that they change places to balance the moisture in a colony over the winter, so that you don't have a lot of defecation that goes on inside. All right, so one thing we should know I think should be obvious to us, that the prime strategy of a colony in the wintertime, and they show us this, right, is the conservation of heat. Now, what they'll do is starting now, and maybe even before now, they'll start to plug up all the air gaps around with propolis. And if you give them an opportunity, you put screen mesh over any hole in the box or anything, they'll just propolize it almost immediately. And of course, we know that they gather in a cluster to transfer body heat around, and we'll show that in a little bit. And then they heat the cluster with thermoregulation. Of course, that's obvious. And then they do something else, which you may not be aware of, that if you allow bees to work in a naturally occurring condensing colony, they will use the hive gases. When I talk about hive gases, I'm talking about CO2, oxygen, and oxygen primarily. Of course, we know that most of the hive gases are nitrogen, but it won't make any difference, because those aren't involved in the survival of bees. They're just part of the ambient atmosphere. But for the hive gases that we're concerned with are oxygen and CO2. Bees in a natural colony, in a tree colony, or in a condensing colony that you might put together and keep bees in, they will use little precise, minute ventilation adjustments on their own. They know exactly what to do to make the environmental atmospheric gases inside the cluster precise in accordance with their biological needs. And then he used their morphology to retain heat, and they do that a lot, by the way, in swarm clusters. But they also do it in a wintering cluster. I'll show you that a little bit. So they have like these little bifurcated hairs on their thorax, and they trap heat like down. And when bees are in tight cluster, when it gets really cold, their little thoraxes are touching, and they've got this little down protection in terms of trapping heat in those little fluffy hairs. Now, they do this in a swarm cluster also, if it gets cold. They do it if it rains in a cluster. A swarm cluster, they hang with a shingle, their thoraxes together in a shingle pattern so the water goes off of them. If the wind blows on a cluster, bees change the morphology of that cluster by spreading out and their cluster over more branches so that they can reduce the mechanical stress on the frame. So bees have lots of interesting behaviors that they use morphology for. And one of them is that they change their morphology for. And one of them is heat conservation in a winter cluster. All right, so bees can lose heat, and we all lose heat constantly, but they heat through conductive, and that's from contact. Bees in the center of a cluster or anywhere in a winter and cluster are in contact with each other. So there's some conductive heat. We'll say loss, but it's because that's how it's dispersed. You saw that in one of the, that single bee and then 5 bee comb illustration I gave you. That's all conductive heat radiating out. Then you have convective heat loss, that's air currents through a colony. If the colony is porous enough, has the right porosity, the convective heat currents will flow through the cluster and take heat away and moisture. And then, of course, radiant heat from the bee's body, which we don't really pay much attention to as beekeepers. We don't really pay much attention to the conductive heat loss either, but convective heat loss is something that we are working on as beekeepers. And we do some good things and some really negative things, I think, sometimes with that convective heat loss. All right, here's some theories that Derek Mitchell came up with. He's a thermodynamics engineer. Most of his stuff is modeling, but he has done some actual work with live colonies, which is what I like, and I'm sure you appreciate. So what he's saying here is that for the most part, during warmer temperatures, a cluster, now I'm talking about the left-hand side of this, is porous. So it has space between the bees because it's spread out more. And that's when convection is most important. And that's when most of the heat is lost through convective currents. But he also is saying on the right side, which is a new concept for us to think about, is that there are temperatures when that beautiful winter cluster is compact to the point where its thermal characteristics act more like a solid. In other words, there's no porous nature to it at all. And that happens under the most extreme conditions. And under those conditions, you're not losing as much heat from convection at all. But under those, what I'm saying as solid on the right is when insulation is the most important thing a colony can have. All right, so that's when it's more important to have insulation than when the colony is more porous and open to convective flows. Right, so that's an interesting thing for you to think about. That there are times when the configuration of a winter cluster may act more like a solid, which means that insulation is extremely important on the outside of the box and especially above them at that point. And also when it's porous, where there's in warmer temperatures, we're not even concerned about bees at that point. So Ed Clark, back in 1918, wrote a little pamphlet called Constructive Beekeeping. This is the one that put me on to the whole idea of what is going on. And he claimed here, Ed Clark, that we're trying to force bees into a ventilation system that they don't really want. And they're trying to show us that they would love to control the hive gases by themselves, but we force them to use a ventilation system. And I'll show you some examples of how we do that. And I think that, and he says that he thinks that the beekeeper will be most sensible person, will see the error of his ways and eventually follow where the bee lead. A great philosophy of beekeeping is always to follow where the bees lead. Observational beekeeping will teach you everything you need to know about beekeeping. You won't have to listen to people like me or anybody else, tell you about bees, because your bees will lead you right there. And I think the bees are leading us in the direction that they're saying, we would love to be able to control our own hive gases. Please leave us alone. We'll ventilate the colony exactly in concert with our biological needs in these little minute ways. And you have no idea as a beekeeper what they need in terms of that. Right. So I'm going to talk now about a ventilator colony versus a condensing colony. And so the basic principle, and there's a good reason for this having become a practice of beekeepers. I'm talking about the ventilator colony, venting colonies. The first thing you can hear, I don't think I've been to a bee club where the first thing somebody is saying in the talk around the audience, around the membership in winter is, oh, you got to ventilate your bees. Yeah, and you got to vent out the moisture, and you got to vent out all those gases. They'll die from it, And so what a ventilator does is it very efficiently vents out moisture. It vents out the gases and cluster heat, and it vents out latent heat, which I haven't talked about yet, but I'll explain that in a minute. So what a condensing colony does is it conserves the metabolic moisture, the gases, and the cluster heat. It conserves latent heat, and it also uses the hive gases to regulate the cluster's metabolic rate. So in a condensing colony, that occurs in trees and in hive boxes that you have insulated and eliminated any top ventilation, and are working, basically have them structured as working like a natural tree colony. The metabolic moisture and gases and cluster heat is regulated by the bees. They're not you didn't put them in exigent circumstances by venting out all of the heat that they're intent on trying to generate. Now, what occurs in a condensing colony is that there's condensation that occurs. And the condensation is never above the cluster in a condensing colony. If it's designed correctly, the insulation on the top of that colony will keep the top above the cluster, above the dew point, and the condensation will form in other areas of the box. Now, when you allow condensation to actually go from a vapor to a droplet, it gives off latent heat. So that's the principle of physics. That's just something we can't change. But the biology of bees over a couple of million years, 100 million years or so of evolution, was to take advantage of that. So bees biologically are adapted to recover some of the heat they lose through the hot, moist air that comes out of their center of their cluster by allowing it to condense and give off its latent heat back. So it's a source of heat that a ventilating colony will just will release to the atmosphere, take it away. And those droplets of water also serve another purpose, because that metabolic moisture that accumulates on the sidewalls of the outer frames, down around the bottom, and possibly on the top where the cluster isn't, is used by bees during the winter to thin honey and get on with the business of trying to feed and eat honey, right? So it's a valuable resource to have water, liquid droplets in the colony in the wintertime. Maybe that's a little counter to your beliefs, but that's what happens naturally. And we've got a lot of data to support this at this point. Right, and then the hive gases are another interesting part. Oxygen's clearly in a cluster that's doesn't have any external source of ventilation except the opening down below. the CO2 will build up to a certain point, and the oxygen level in the middle of the cluster will go down. Now, when that happens, it changes in insects, unlike human beings, which would die from too much CO2 around. It changes the insect's metabolic rate. So another biological adaptation for bees in a winter cluster is when they experience a higher level of CO2, the response, the biological response, is to reduce their metabolic rate, because under those circumstances, when the CO2 is building up and the oxygen's going away a little bit, they are in a deeply cold environment, or it's where they have to do a lot of thermoregulation. So that's their response. They don't die of hypoxia. That's a human disease or problem. Winter cluster, simply the bees just change their metabolic rate and they conserve the use of honey. So if they're allowed to do all those things in a condensing colony, they're taking advantage of their biology. They know exactly what to do. They know exactly how to ventilate the colony also, with minute little wing movements at the entrance or around the outside of the cluster. All right, so why did that happen? Well, I mean, it's pretty clear to me that the porter bee escape hole probably advanced our thinking about making sure that colonies have lots of ventilation, because of course the water will condense on the cold surface and drip back down to bees. So the natural knee-jerk reaction to the lineage of bee lore was to ventilate the colony, and it works. If you ventilate all of that stuff out of there, you won't have any moisture. But you also, if you pay attention to the last slide, you put the colony, as Derek Mitchell would say, in constant stress survival from stress-related heat loss. All right, so we know that bees can, so that's it. So then here's ventilation equipment. And I mentioned to you before that bees will ventilate their hive gases in small increments. And I've always thought that if we could figure that out and make a ventilation system that manages the ventilation exactly the same way that the bees would have it done, then maybe that would be something that might take some stress off the colony in terms of their minute changes in the hive gas structure or hive gas mixture in a winter cluster. But we don't know that. So what we do is we put a lot of ventilation in, and way contrary to what bees will do naturally. And these are some of the devices that we use, and you can say, hey, well, I just put, beekeepers will tell you they put wedges under their front cover, and there's these wonderful little cloak boards that you see there, all with ventilation holes in them. And some people will put one of these on and then insulate over the top of that, which is absolutely useless thing to do, because of course you're letting all the cold air in onto the frame bars below the insulation, which has nothing, it will do nothing, right? You don't put insulation and cold air together. All right. All right, so how much ventilation do bees need in the wintertime? This is sort of an extreme example, but here's some single deeps loaded with snow. And yeah, there's no ventilation here at all. Nothing's going on. They're actually in these mounds of snow. Bees will actually find a way out of that colony under that snowbank and make a pocket in there where they can do their cleansing flights if it gets nice and warm, and they can take a cleansing flight there. But when the next slide will show you how, there's bees are perfectly okay after a long time under that snow. Right, so now that snow is very porous, by the way. So snow does not act as a like ice would, which would cut off that ventilation piece that occurs naturally in snow. Of course, we know that snow doesn't kill organisms that are below it, because in the springtime we wouldn't have anything left, right? So any little insects that are burrowed into the ground a centimeter or two survive just perfectly with their own metabolic gases that are just permeate the snow level and go up into the atmosphere. So yeah, so they don't need a lot of snow ventilation from with snow, except we all know we go out and we do this, and I still do it. I go out and I make sure that front entrance is open, especially if there's an ice storm or something like that. All right, so and here's bees trying to tell us something, and they use propolis to close up all the holes. That the top one is a hole somebody drilled in a good box, and then the bottom one is a porter bee escape hole, which had a telescoping cover on top of it, and you can see there they built a little moat of propolis and wax to cut off the airflow down through that porter bee escape hole. And here's another propolized screen on a regular colony. Now we've bred or tried to breed and successfully bred the production of propolis, except for some colonies that revert back to it. But most of our colonies don't produce anywhere near enough propolis, in my opinion. The Caucasians were the bee species that we brought over earlier in our quest to bring over Western bee stock, and Caucasians were noted for building a lot of propolis, but then we don't use them anymore. So the bee stock in our country is about 40% Carniolan and 40% Italian, or somewhere in there, in that area. About 80% between those two subspecies of bees. All right, so here's an example of what I was suggesting before, where you can see that red outline is where the cluster is. Now, this top that you're seeing on the left is a top that's right over that those colonies on the right. I just pulled it off, and just to illustrate that the moisture never really ever, as long as that colony's insulation top is above the dew point. You can see that in this case, some of the condensation formed on the outside ring of the top. Now, lots of times if you allow the bees access to that insulation, they'll winter on that surface. So I've had to do things in my colonies to keep them from doing that, so I could look at them without dropping a big blob of bees in the snow. But anyway, yeah. So if you practice condensing colonies, you find that your bees will live up higher in the box all winter long. The center's dry. The outside peripherals got a little bit of liquid moisture. Remember, that gave off latent heat when it formed droplets. So some of the heat is recovered by the colony. It's also available for them to use during the winter to thin honey and eat it. All right, we talked about all of this, except the data out on what occurs if in terms of the latent heat loss. It requires about 12% of the honey that bees have collected during the winter for survival. So just that one little thing that you might think is insignificant, the fact that vapor goes to liquid and gives off heat, represents about, if you ventilate that out, you lose about 12% of the honey that the bees have stored. And then that puts ventilator will put something in the constant survival mode, and of course you can read the rest. I didn't stress at all about heater bees suffering from oxidative stress, but they do. So they may live less time. They sacrifice their musculature for the benefit of the colony. And of course, small clusters experience significant stress under any conditions, by the way. But especially during trying to thermoregulate with, especially with, if you ventilate small clusters, you might as well. It's hard to keep them alive, let me put it that way. And then I'm trying to sell the condensing colony here then, but we talked about all this already, and then just to emphasize that elevated CO2 induces an ultra low metabolic rate. So everything, as far as I can tell, in a natural, and there's some really good support for this. Tom Seeley's doing some great work with it. As I said, Derek Mitchell, Etienne Tariff, there's plenty of people that keep bees in really, really cold places, which use condensing colonies as their go-to for winter survival. All right, I talked a lot about this. There's really no reason for me to go over it again. It is an illustration from a friend of mine, Randy Oliver, out in California. And, you know, I talked about maybe the core bees are dehydrated, maybe the mantle bees have a little bit more moisture in them and they change places to balance that out. And this sort of shows you in the center, that red buck in the center is that when oxygen and humidity are going down, temperature and CO2 are going up in the core. And whereas you might think you have to get that bad air out of the colony, truth of the matter is that bees are biologically adapted to control that those hive gases to the extent that they take advantage of their own metabolism's ability to regulate its processes based on high CO2 and low oxygen. All right. Oh, I think I pretty much covered most of this already. So this is a study that came out a long time ago, and this one just sort of proves that hypoxia is not a problem for bees, and also that how bees regulate their cluster with their reduced metabolic rate. And what it does, it conserves moisture and food and keeps them in an alert state and with energy savings and longevity. So great study by Brulins back in 1997. This stuff has been around, but I don't think we've been paying much attention to it. There's a difference between a bee colony that I took out of an old tree here in Connecticut. You can try to see the difference between the thermal mass that a colony in a tree versus a thin 3/4 inch Langstroth box provides. Probably about, according to Derek Mitchell's calculations, the way we keep bees in a thin wooden box without any insulation around it, it provides 7 times the heat loss that a tree colony would experience in any old tree it's in, if it chooses the right cavity to be in. All right, again, so I'm at the point where I'm summarizing this thing, and I just want to illustrate again, this course is more of Dick Mitchell's work, but it's actually Etienne Tardif's figures, his interpretation of it. What it shows is from left to right. It shows that if you have an uninsulated box and a top entrance, the large arrow is the flow, the airflow through the colony. And then you'll notice that there's a very minimal amount of heat dome, which I haven't gotten around to talking about again since the beginning of this talk. That heat dome is above the cluster and it's being lost out of the top because it's just a small wooden uninsulated top. All right, so the size of the arrow give you an indication of how much heat loss occurs in the different configurations. So you can see the one on the left, big arrows on the sides, a medium-sized arrow with the top hole, the ventilation hole, and then the big arrow on the top, where about 75% of the heat is lost in an uninsulated colony out of the top. Now, if you were to take that same colony and insulate it and leave the top entrance in, you're still drawing air up from the bottom and chilling the colony. But you do have some benefit that the heat dome is a little bit stronger, and you're not losing, of course, as much heat out of the sides or the tops. But the ultimate configuration would be the one on the extreme right, where you have lots of insulation on the top, where you mitigate against the largest portion of heat loss, and on the side. But what's important for you to note there is that the airflow changes. So heated air is now dropping down and exiting out the bottom. So for the most part, your condensation occurs below the clustering bees, or if it does occur on the top, it's outside the area of the cluster. And so that's the takeaway from this. Change the way that the convection flow occurs in the colony, and you put it into a more natural state. All right, so that's the takeaway. All right, now I'm not going to go over these very high. This is Steely's work, and this is an ABG of 2022. He's not going to put live bees in these, but again here he looked at tree cavities versus uninsulated box, and you can see tree cavity is it's hard to show you. It's that straight line on the 0 Celsius. That's the tree cavity's temperature as the ambient temperature, which is the the blue, and the wooden box, which is green. This is an empty box now. So this is just the start of Seeley's look at this, showing you the different fluctuations in temperatures during the day. Wooden box changes almost in concert with the ambient temperature, all right? But a takeaway again on the tree cavity is homeostasis, stability. That's what bees want. Bees, in order for bees to control their environment, they want it to be stable so that they're in control of the hive gases. All right, so same thing. This happens to be an insulated box. And if you'll notice that the insulated box, then the green line changes a little bit differently. Again, the tree cavity wins for stability. Now the insulated box will get a little bit warmer, but not much. If it was 0 degrees Celsius outside, or a little bit 5 degrees Celsius or something like that, according to this chart, you'll see that the green box goes up. But of course, then it dips at night, again, to low temperatures. So again, fluctuation in the amount of temperature variation in those configurations, but in the tree cavity, fairly stable. All right, so take that as a baseline. Well, what Seeley took away from this is that it's clearly a winner. Tree cavity is clearly a winner, but you can make your box into a tree cavity-like device. All right, so there are some insulations you can use if you're deciding that some of this talk made sense to you and you want to try insulating. There are foam boards. Some people are a little bit opposed to those foam boards because, of course, they're expanded polystyrene or they're polyisocyanurate, so they're an oil product. So you can spend a lot of money and use wool if you want. Comes in rolls if you can find this, or you can have sheep near you. Sure, a farmer will give you a bunch of it, and you can pack it into a cavity that you make, or some other way that you form it around the box. I just want to let you know that there is wool as a natural way to insulate your colonies. The beekeepers that make lanyard hives, that they use wool exclusively. All right, what's not insulation? Well, I think a lot of people think that black roofing paper, basically tar paper, is some kind of insulation. It isn't. It can act as a windbreak if it's properly installed, and it might keep air from infiltrating the cracks, but it doesn't have any it doesn't have any mass, so it can't be R value. It has no R value at all. Most wood-based quilt material, I don't know, quilt box material, that's absorbed moisture, which eliminates any insulation processing. So quilt boxes are an interesting study. I'm writing an article on them now. They were basically designed and used initially in worry hives But in warrior hives, they weren't so much about insulation as they were about other reasons, which I'll write about in the ABJ article. But as soon as whatever material you put in a quilt box starts to absorb moisture, it absolutely eliminates any insulation property it might have had. Right. So most commercial wraps, I don't know about them. They usually have R value. Homosote, which is a cellular fiber. So that was old school stuff. Put a slab of homosote over the top of your inner cover in the wintertime, then change it when it gets really damp and wet. I think people thought that might be insulation, but it isn't. It's only it was only a half a R to start. And so that's, if you compare that to the 7 or 8 R per inch capabilities of the EPS foams, comes nowhere near being an effective insulator. Anyway, it has copper metaborate, which is a toxin to bees. So unless if you're insistent on using homosote for some reason, you got to get the kind that doesn't have its preservative. See, remember, homosote was designed as a building envelope. By the way, my specialty in my engineering pursuits, professional pursuits, was building bay insulation technology. So I was a consultant for some major projects where I was the one who designed the insulation applications to make those enhance the thermal properties of building structures. So that's what I've taken out of that professional career and brought over here to beekeeping. So that copper, we don't know what it does, but it's toxic to bees. And it can be, so you can see by that study down below that if the heavy metals accumulate in bees as they chew on that homosote board, it can give them toxic effects, sublethal effects or something like that. We never know. No one's ever looked at homosote colonies and said, well, 10% of the bees died from too much copper, residual copper. There's no study, so we don't really know. But I just think it's a bad idea to put an insecticide above your bees when they're trying to winter. All right, quilt boxes are there. And then I wanted to let you know, and I think you know this anyway, that there's a bunch of products that are coming out now. There's some from Australia that just hit the market. There's all kinds of products that you can buy at this point. The movement, in my opinion, in beekeeping is to complete insulated boxes, whether or not it's for the belief in condensing colonies, or if it's just, wood's scarce and is starting to make them out of plastic. But whatever that reason is, these functions they function beautifully as a condensing colony. So if you don't want to go through the process of making sleeves like I did back in 2015, and I still have, and you want to start off with a condensing colony, there's plenty of choices for you. This was April Monday in Montreal. When I was down to Chile for last year's April Monday, or year before that, April Monday, and the same thing, rooms after just loaded with colonies with thick insulation around them. All right, but if you decide that you want to, so here's a sort of match between an insulated colony called Hive IQ and one that isn't. And so these two boxes are matched for population, and the implication here is that the box on the left, highly insulated, will allow bees to stay inside and regulate the temperature. Whereas if they are not in an insulated colony, they beard outside the box to do the same thing. So interesting assertion, but I'm not sure how true that is, but you can see it here. And I have seen some of the other insulated boxes out in the Gibson Desert in Australia. Bees will stay in them when temperatures get intolerably high because they're are capable of being able to regulate the hive gases better than if they were outside the box in 135-degree temperatures. All right, so let's see, there's how I made my boxes when I first started out, and I still make them today like that. If I have a Langstroth box, I build them out of a foam insulation, and I use a reflective surface on my foam because I hadn't talked about this till now. But this is the last slide. We might as well talk about it. If you have a reflective surface over the top of your bees, it will reflect some of the infrared radiation that's lost off their warm bodies back to them. We don't have any real scientific numbers, but I know from my building envelope experience that in some insulation applications, all we used was a thin foil to reflect radiation back out of a building wall or a roof joist cavity to keep the inside surface cool. So it does work to reflect IR back to the bees. How much? I don't know. I can't make any claims for it. I just like doing it because I know it's a principle that works. And I buy this foil faced insulation. So as soon as I make the box, I have a reflective surface to go back on the bees. When it's done, like it is in the upper left, it's completely insulated. And the insulation on the top cover hits the side covers. So if you look at the photograph right to the right, you'll see that what the bees are looking at is a complete seal of insulation around it. And then I put that screen in the top to keep bees off of that shiny surface because they live on it during the wintertime. All right, so that's about all I have. So did we get any questions there?
Yeah, Nancy asked, at what temperature do bees die?
They die at about 43 degrees or 42 degrees. If they stay that way for like 50 hours, they'll first go into a chill coma and then die. So if they can't thermoregulate for some reason, if they get too small, right, they'll live for a while, but then they die. I mean, if the cluster gets too small.
I have a question about your boxes.
Oh, did she say, did she mean low temperature or high temperature?
Nancy, go ahead and unmute yourself. If anybody wants to unmute yourself so you can ask a question, feel free.
All right, so
Nancy's still here?
maybe she meant high temperature.
She might have left already. Okay,
right, yeah.
sorry about that.
All right, no problem.
Okay. Feel free to unmute yourself if you have any questions. I do have a question about your box that you made.
Oh, the one I make, yeah.
Yeah. Now, are you surrounding a wooden frame or is that?
Yeah, that's just a regular Langstroth box in the middle.
Okay.
So see the picture on the left there?
Uh-huh.
There's a sleeve that goes over a regular Langstroth box.
Okay. Okay.
There's these little cleats I put on. I don't know if I can show you this. You see this little cleat there?
Right.
I added that little
Okay.
cleat just as support for this box so it doesn't just flop down and cover the
Okay.
entrance. Right. So the entrance is in under an inch and a half of insulation.
Right. Okay. Gotcha.
Way in there, right? There's a mouse guard in there also for the wintertime. And so that's the way I did it when I was making them. But you can make them out of, you don't have to make them out of this foil insulation because it's expensive. You can put foil on EPS if you wanted to make it that way. And you can make these out of EPS, which is a cheaper alternative. If you wanted to make them. Making them is hard because you have to make a special telescoping cover to get this done because you've increased the width and the length of the hive body by the thickness of the insulation.
Okay.
So it's a little bit difficult to do. You can, of course, make the top out of just a single sheet of EPS if you want, and put a rock on it, it would work.
Oh, okay.
All right.
All right, I have a question on I've seen some people will take the old inner cover and then they'll put like 1.5 inches of styrofoam insulation on top of that and put their inner or their telecover on top of that. Is that all right? So you still have that inner cover surface. I presume, is the insulation going to keep that surface warm enough so it won't condense the
Yeah, usually,
moisture out?
yeah, it usually does as long as you keep all of the ventilation stream out of that top cover. A lot of inner covers have that little notch out of the front of them.
Yeah, yeah, I don't
Gotta
like.
plug that up, and then keep the yeah. You can do it that way. You can also put the insulation right down on the top frames and put
Yeah,
the
because right now I've got some old candy boards that they're 3 inches deep, and I was either thinking about either putting 1.5 inch insulation. It's got candy board with like a 1/4 inch piece of luan, the same size as your normal box. If I took the inner cover off and shoved 1.5 inch or 2 inch insulation up into that candy board, it would. I'm also looking at the space between the frames and the insulation, whether it should be inch or 1.5 inch, possibly 1.5 inch to put like let's say a sugar brick on there if I have to. But you were also saying putting like if you put a screen inner cover on there, that'll keep the bees off the insulation too.
Yeah, you see that little screen, like that's an emery shim or Mary
Right,
shim, which it's screened on the opposite side. Right, so it's not screened down against the frames.
right.
It sits on, so it gives you a little space to put that feed on if you needed to.
So yeah, I do have some emery shims. They're kind of they're not very tall, but that would work.
No, they're about, so these I of course cut on I said this once and I was criticized. I said I cut them on my table saw, and I got from the audience, well, who has a table saw? Not everybody has a table saw.
Doesn't everybody have
I
one?
thought everybody in the world had a table saw. They
That's
don't.
right. That's what I say. They come to me wanting to do a wood project.
Yeah, they'll make you cut them, Carl.
And then I say, well, asked them what machines, well, they haven't got anything. Well, I said, how were you figure on doing the project?
Yeah, can't do it. So if you have, so I put I put, galvanized number 8 hardware cloth.
Yeah.
And so all it does is it rests in that. If you notice here, the way I did it, and you can modify this, you could probably come up with a better way. This sleeve is proud of the frame. This is the frame rest here, right? It's proud
Yeah.
by 1.5 inches. So this slips right in. You can see it here slipped in. There's still about 1/2 inch of foam above this emery shim with the screen on it. So that when you put this telescoping cover here on top, it makes this complete box. The sides touch the top.
Yeah.
There's no ventilation except for the bottom. Right. And
Okay.
when I first started to do this, I ended up with bees living here on this surface. I mean, even if you put your hand on that in the wintertime, it feels warm because it reflects your body heat back. And they're the same, they act exactly the same. They come right up and they live on under that, and they get their own body heat reflected back to them, and they're just living there. I thought at first they were all going to die, but it turns out that that's what they just do naturally. They live on the warmest surface they can find in the box. That makes a lot of sense to me. Why would they stay in the cold comb if they can move up against the top of the box, which is really, really warm because it has a lot of insulation on it.
Mhm.
So yeah, you can be a lot of creative, figure out some creative way to do this. Now, if you wanted to buy, if you did make a cover, you can get I forgot see, I'm going to have to write this. The cover that's sold, B-Max. You remember B-Max when it first came out? It was a poly
Right.
hive. Well, the
Right.
cover for B-Max hive fits over this sleeve. So you wouldn't have to make anything. You can buy a B-Max cover and it'll fit right over this sleeve. And you have a nice insulated 1.5 inch foam cover that comes right out of manufacturing. So you don't have to make a special telescoping cover. The most important thing you can do for bees in wintertime is top insulation. We all know that.
Top insulation?
Top insulation is, if you're not going to do anything, don't ventilate out of the top and give them top insulation, and you're giving them a good head start.
Okay. Donna has a question.
Yeah,
She said, I use insulation on 3 sides, but leave the front so I can use the FLIR. Is the insulation useless? My bees seem to like it and they
yeah.
do use less food.
Yeah, the insulation on the side at that point is useless. Because what happens is heat goes to cold. So if you have one cold surface, the heat will just go out there. All right, so the side insulation is not working, but the top insulation is in that case, if she insulates the top. Now, yeah, I get that with the flare camera, it puts it out of action. And I hate that, but because it's so much fun to see where the bees are.
Yeah.
During the winter time, you can do that. Yeah. So think of something else like a little cutout of that insulation that you can take off and then use your flare camera. that
Make
way.
a peeky hole.
Yeah, but it has to be fairly big,
Yeah.
and I use the foil tape on this, and you can actually, you could make a side out of foam, cut out a fairly good size square in it, tape it up with the uh, foil tape. When you want to use your flare, you just bring a little knife with you and slice the tape, and it'll flap down like a door. And then you can tape it back up. The thing about insulation is whenever you compromise any part of the envelope you're trying to construct to keep heat in, it compromises the whole structure. So you're better off trying to keep it as intact as you possibly can.
Okay. And then you mentioned about screen bottom boards.
Yes.
And that is okay or not okay?
Well, so if you're going to leave your screen bottom board open all winter, it's probably not a good idea to leave it that way. I slide a piece of Luan in the bottom of mine just to keep the drafts off. Because remember, what we're trying to do is conserve the heat dome.
Right.
And the bottom of the colony is pretty much at ambient temperature. So it doesn't really, but I don't like the idea of a wind gust or something coming along and trying to find its way into that screen bottom. I don't think it can get in there because there's actually a high pressure area that forms in the colony with that heat dome. So there might, so there's some resistance to air coming in and wind, but I just don't like it.
Mm-hmm.
So I try to cover it up.
Yeah.
I get good survival rate with with condensing colonies. Anyway, to me, it makes more sense.
I agree.
All right.
Any other questions? Speak now.
Yeah, I got a question. Bill, thanks a lot for the presentation. I've been following this approach for winter for a few years and have had really good results. So if anybody's on the fence, it works.
All right.
So for anybody who goes through the investment and effort of maybe insulated top and maybe some of the additional insulation, I know our focus is winter, but do you have any thoughts on leaving some or all of the insulation in place?
Yes, I leave the only reason I take off the sleeve is for ease of inspection during the winter time. And during the summertime, we got to do a lot of that these days. If like I had to fight small hive beetles all year long, and you couldn't have a sleeve that you had to keep taking off to figure out what your traps were doing or how much you were dropping larvae out of the colony. Just has to come off for any other reasons too. You want to expect this queen, right? But I never take the top insulation off. I run that all year long. It works exactly the same in the summer as it does in the winter. It keeps the colony's top cooler. So bees have an opportunity to regulate when they're heat stressed, they still have an opportunity to keep some heat out.
Gotcha. So not ventilated in the summer, but just the insulation.
Yeah, no ventilation for the top. I never run top ventilation at all. No top entrances in any of my colonies.
So kind of like your roof and your insulation in your roof.
Yeah, you wouldn't take that off in the wintertime, in the summertime, right?
Yep.
You wouldn't
Thanks.
take your roof insulation off in the summertime. Just like you would You wouldn't take it out of the walls in the summertime either, but in
Right.
this case, you gotta take the sleeve off.
Right, okay.
So I guess you keep your screen there on the top as well, so that they're not chewing up the insulation on the top?
Yeah, that's a problem with them little devils. They'll chew it up. So you can paint it with latex paint if you wanted to, and that'll keep them from chewing it. And yeah, I take the screen out because I'm not going to be feeding, but and I like to put, and I adapted the use of canvas for inner cover, and I just loved it. I mean, it gives you lots of flexibility about how you can tear it off a couple of frames and just do a little inspection in the corner while the rest of the bees are all nice and quiet under the canvas. So it makes for a really interesting way to keep bees calm during inspections. But of course, you can't use that canvas with small hive beetle infections, because if you're going to put traps on those top frames, it doesn't give the bees a way to get the beetles into the top of the tracks. You close them off. So you got to go back to a hard inner cover. So I was disappointed this year that I had to go back to those, but I like that canvas cover better.
But if you're painting the top, aren't you doing away with the reflective material?
No, it's underneath. So IR will go right through the paint.
Okay, thank you.
Right. Any other questions?
So you can paint it with aluminum paint too if you wanted to, Jay. If you want to go crazy. I mean, when I give this talk, beekeepers teach me a whole lot. They say, "Hey, can't you do this?" Yeah, you can actually. Now I think about it.
Oh,
All right, guys.
all right, well, thank you very much, Bill. This was great. I really appreciate this. I'm gonna
Yeah.
put it to practice this year. for
Yeah,
sure.
we'll give it a try. I mean, and let me know how you make out. I mean, I've gotten a lot of feedback. This is going on all over. These articles have gone out to different journals in Greece and in England and in the Netherlands, and I get feedback from a lot of them. Of course,
Wow,
in Europe, they've been doing this for a long time.
yeah, well, that's great. Very good.
Cool.
Thank you very much.
All right, we'll see you then. Thank you.
Okay, take care. Thank you.
I know.
All right. Okay, anyone have any questions or issues they want to address with their hives getting ready for winter? Unshare here. Whoop. Sharing. Okay. Oh. Anybody have anything? No? Okay, you can unmute yourself too if you want. Oh.
So is it too late to combine two colonies?
Oh, Charlie, what do you think?
What do you got? A queenless hive?
Yeah, I went in and made sure after I did my mite treatment that all my queens were laying, and I have a hive that I don't seem to have a laying queen. So
Yeah, this weekend's supposed to be 70 degrees. So yeah, go ahead and combine them. I did that last week, I guess it was. And I had, like you say, you had plenty of bees in there. You had some stores in there as far as honey goes, sugar water honey or whatever. But there wasn't any, actually I had seen some queen cells. Obviously that wasn't going to take. So there wasn't any brood or anything left. So I put the boxes that were full of honey on other nukes and shook the bees out in front on a ramp, let them walk up into the other hives.
You made a video about that, didn't you?
Yeah, that was that was about a week ago I did.
Yeah. If
Yeah.
you happen to
I had another video several months prior to that where it really showed them walking up into the hive and letting them in. I don't know what the difference is about that, but they seem to get along better when you do it that way. Depends on how many bees you got in the hive too.
yeah, so I mean, I have one hive that's not very well populated, but has a fairly.
Well, then maybe just, put a
But that
box on top of the other hive that you want to combine as a funnel. Just shake the bees off the comb if it's empty comb to begin with. And all that.
Okay,
I mean, they don't, right now, I don't think they're going to be fighting too much. Most of the time they don't fight anyway. That kind of a thing. But yeah, I would do it this weekend. All next week it's supposed to be in the 70s during the daytime. Perfect temperatures to do that kind of stuff and all that. My hives they look just like, they're exactly that. Last Saturday, I guess it was, is when I finished up feeding. They had drained all the feeders that were left, took them all off and closed them all up and put in entrance reducers in all the 10 framers they got entrance reduced down to 4 inches for robbing purposes, which I really didn't have any robbing problems except when the feeders were on. And, yeah, my question as like tonight, I've got these candy boards that are 3 inches deep. And I'm like, well, I'd like to put 2 inches insulation in there, and then it gives me about an inch gap. And or should I only put 1.5 and gives me 1.5 so I can put a what do you call it, a sugar brick in there? But I don't foresee me having to worry about that because number one, they're not going to eat as much honey if they get the insulation on top.
Right.
That should run out, and I feed mine to the point where this year was like a perfectly timed it where they took, as they got to the point where they weren't taking anymore, I kept leapfrogging my feeders from one to the next and pouring what wasn't used by the one that was at full and poured into the one that was still drinking. So it all turned out good. I just need to get myself a sheet of, I think I'm gonna go ahead with the 2-inch insulation and try that this year.
I did do the top insulation last year and I thought it worked very well, but I did have problems with trying to keep it on in the summer that they started chewing it up. But as Dina said, that painting it, and as he said, paint it. I haven't painted it yet, but that was my intent.
Yeah, one thing I did do this year, I got 2 screened inner covers where they're totally screened without a notch and everything. And that, I'm not sure whether the insulation keeps the hive, he says, cooler and all. I don't know. And then we had them really severe hot days. I've got some ventilation shims, or I bought them when I first started. And I put them on the hives just to kind of give them more ventilation, and it kept them from, bearding considerably. So I don't know. I've never had insulation on top, but on the other hand, I've always had good results over the last 15, 16 years.
Knock on wood.
I don't know. I'd like to try the insulation, I think, this year. See how it goes. I did have a licensed all insulated hive. It didn't have any upper end of ventilation, and it worked just fine. And when you use in those hives, those bees won't, they don't react to the fluctuation of exterior temperatures where you're going from a 40-degree to a 60-degree day. They don't feel that range of fluctuation of heat. It takes them several days to react to that if it continues to be 60 degrees outside before they fly outside and all that.